Lecture 1.13 is on question number 2 of Honors Calorimetry Expanded Problems. You have the key in the website under the Files page, but I am going to walk you through the problem on number 2. Number 1 we did together, and let's get started. So in number 2, what we're going to do is first define where energy is flowing. That's most important here, because with trying to read this problem and not drawing a diagram of a heat diagram, it's very difficult. Okay, so I know that I have a container, which is my styrofoam cup. My styrofoam cup is going to represent, all right, the place where the water sits in. Not a very good drawing, but nonetheless, here's the water, and we're going to have a block in the water. Okay, and the block won't be floating. Now our block of copper is at 10 degrees. The water is at 45.0 degrees. Okay, so clearly we are going to have a flow of heat, and I'll use the red for the heat, and heat flows from hot to cold, and we're going to have energy flowing from the water to the block. But we're also going to have flow of heat from the styrofoam cup to the block, or the styrofoam into the water. It's not going to matter, because if you lose heat, okay, from the water to the block, you're also going to have a temperature gradient for heat to be lost from the cup to the water. So two things are happening. Both the cup and the water are both losing energy. So both of these are losing energy. Okay, well, who's gaining? Who's gaining? Block. So those are our three components. We have someone losing, or we say releasing heat, and somebody absorbing. I'm stuck with the absorbing definition because physical warming isn't really a consumption, it's really absorbing. So the energy, or the Q that's released, equals the Q that's absorbed. And who's getting released is the cup and the water. All right, so let's get rid of some things here. So it's very important that we define the energy released and absorbed. As I always keep saying, or as I've kept saying this unit, you can't have exothermic process without endothermic. The energy is going from one system or one group of compounds or things into another. So in any case, as we said, who's gotten released, okay, is the cup and the water. Who is getting that energy from them is, of course, the cup. If I can spell that. Now, it's not the cup. Scratch that. The block. I can do this. All right, so here's the block. Now, again, some people might say to me, Mr. Krosky, I'm kind of confused with the flow of heat. And if I was to zoom in this cup a little bigger, and now I have the block here, okay, clearly the heat, okay, is coming in from the water to the block. And I'm sure there's some direct flow of heat from the styrofoam to the block. But if you think, also you can have some heat flowing from the cup into the water. And it's the same heat if you think about it, because if some of the energy from the water goes in the cup, that means the water now is cooler, and the warmer cup's going to warm it. So it doesn't matter if it goes directly or into the water. There's an overall flow of heat toward the cup, collectively by just the water alone or the combination of the two. All right, so the bottom line is these two parts of the Q releasing are the cup and water, and the block is absorbing. We're not going to use the negatives for obvious reasons. Here we go. So Q of the cup plus Q of the water equals Q of the block. Notice the plus. The heat released by the water plus the heat released by the cup. We have to consider the cup losing heat. And you may say, well, how do I know the temperature of the cup? Well, we can make the assumption that if you have a cup with water in it, the cup is going to achieve the same temperature of the water if it's sitting there long enough at the same temperature. So if I had a room that was 45 degrees Celsius, the water would be 45 degrees Celsius, and of course the cup would also be at that time. So those are the kind of assumptions you're going to have to make. The cup and the water are at the same initial temperature. Obviously, if they're sitting long enough, they will be there. And I may say, well, they're getting cooled. It doesn't really matter if they're getting cooled. At that point in time, at 45 degrees, at that point in time that was measured, this cup and this water were the same. Okay, moving on. All right, so what's the Q of the cup? Well, it's the mass of the cup times its specific heat times its change in temperature. Okay, and same thing here. Mass of the water, specific heat, change in temperature. Same thing here, MC change in T. Now we got to evaluate this change in temperature, okay? Because as I said before, we're not using negatives. In AP, we'll talk about the negatives by who's gaining and who's losing. We're keeping the absolute values of these. So what we're going to do is think about what's happening. We have the warmer water, okay? So we got the H2O and the cup, we'll put them together, are warmer. So they're going to come down in energy, or come down in temperature, I should say. And then we have the colder block, it's at 10 degrees. And of course, that's going to come up. So we're trying to find temperature final. The temperature initial for the water in the cup is obviously higher, and the temperature initial for the block is definitely lower. Okay, keeping with that and trying to keep these values positive, the change in temperature is going to be evaluated by the difference of the final and initial. Since the cup and water are at a higher temperature initially, we're going to go Ti minus Tf, just to keep that positive. Okay? And of course, since the cup and water are at the same temperature, it's Ti minus Tf. And the higher number minus a small number will give me a positive value. Over here, we have the opposite. The initial temperature is going to be smaller. So what we're going to do here is temperature final minus temperature initial. And that'll give me a positive value because the final temperature is going to be higher. The block's going to go up in temperature. Therefore, bigger number minus a small gives me a positive number. Okay, so I'm just going to erase this change, and I'm going to put in my values. And at this point, we are at the end of what really is the chemistry or the physical science. Okay, Ti minus Tf, and of course the idea behind the problem, and this is parentheses, they're all in parentheses. Okay, the idea behind this problem, this is a plus, another parentheses. The idea behind this problem is we're trying to find the final temperature, that they're all going to be equal once they reach equilibrium. And this would be Tf minus Ti. Okay. Get rid of these guys. Let's put some numbers in. And away we go. So the mass of the cup has to be given, and of course it is. We have a 10.32 gram cup. So I'm going to change my ink so we can follow along. 10.32 gram cup. All right, the specific heat is of the cup, okay, is 1300 joules per kilogram. And as I've been doing, I'm making you convert joules per kilogram per degree Celsius. Going to get rid of kilograms because I want to be in a unit that'll cancel. And this is 1,000 joules equals 1 kilogram. Kilograms cancel. I'm dividing by 1,000. This is 1.300 joules per gram per degree Celsius. So I'm dividing by 1,000. So that's 1.30, 1.3, and that's joules per gram per degree Celsius. I'm putting the units in right here so I make sure that my setup is correct. And of course, the next thing I have is Ti, temperature initial, which was 45. Okay, I'm not really caring about the precision here. Minus Tf, That's what I'm trying to find. Okay, this has to be plus. And now we're over here for the Q of the water. Not leaving enough space I can see. The mass of the water was, we got mass of the water is, well, they said the amount, the volume of the water was 320 milliliters. So it's going to be 320 grams. You may say, well, why? Because the density of water is 1. So 320 grams because the density of water is 1. Specific heat of water, we're going to be in joules, is 4.18 joules per gram per degree Celsius. And temperature initial, again, is still 45. Okay, degrees Celsius minus TF. Everybody on the same side will have the same type of value there. Okay, equals what? Well, the mass of the block, which was 0.344 kilograms. I'm just going to make everything grams for simplicity's sake. I know that I could change possibly or leave the units the same, let's say in specific heat, but I want to make it into grams, and you should understand that's clearly 344 grams. I'm just making sure, I'm just keeping things simple. I know that I can use kilograms if I use the kilograms of the specific heat, but what the hey. All right, and we have a specific heat copper is 380 joules per kilogram. Well, I'm dividing by 1,000 by the same conversion. So this becomes 0.380, and because you've learned about this, it makes sense that its specific heat is smaller, okay, than, let's say, styrofoam, who's terrible, and this, of course, is grams per degree Celsius. And hopefully I have enough space, which I'm running out of. My TF is what I'm solving for, and that's minus whatever the temperature was for the water, or the block, I'm sorry, because we're going to the block, is 10 degrees Celsius. Okay, and there is my setup, and the setup is done. Okay, now it's just math. Okay, now I got my calculator with me. Okay, so 10.32 times 1.3 times 45 is 603.72. At this point, I'm going to get rid of all the units to clean things up. The units kind of help me to recognize what I needed to have. Degrees Celsius, grams, so forth, joules. Everyone is joules. You notice if you were to use kilojoules, if you kept this to be 0.34 and this kilojoules, you'd be solving for kilojoules over here, and it really would mess up the values. Everything's got to be in the same unit. You want to pick all joules, all kilojoules. So it's understandable that these units are here to prevent those mistakes. Okay, so 603.72, and of course, what I'm going to do here now is take 10.32 times 1.3 times negative 1. Well, negative 1, that's negative 1 there, and I get negative 13.416, and that's TF, temperature final. Okay, and now, of course, I can remember I'm adding this to this side. So now we got a lot of simplification here. So 320 times 4.18 320 times 4.18 times 45 again, I'm sorry, is 60,192. Okay, and throw in this minus sign in because it's going to be a minus number. 320 times 4.18 times negative 1 is going to be negative 1337.6 TF. Close that parentheses, equals 344. Let's clear this, my calculator. 344 times 0.380, and this gives me a positive 130.72. Okay, TF, temperature final, minus 10 times this number, all right, 10 times those two numbers, so that'd be 1307.2. So I cleaned this up a little bit, rewrote this and color coordinated a little bit so we can clearly see what we're doing. As you can see, the Q of the cup values are here, Q of the water here, and of course that equal sign we're carrying. This is the block information. And we, as I just talked about, we distributed through. For those that still kind of lost on how I did that, very simply, I distributed 10.32 times 1.3 times 45. That got me this number. Then I did the same thing, 10.32, 1.3 times TF. Notice it's a minus TF, so they give me a negative value with the TF ending. Okay, so this times this times this gives me this number. 324.1 times negative TF gives me that number. The same kind of distributing of the values through. Any case, let's simplify. So we're going to now color coordinate this even more. Why not? And what I'm going to do is I'm going to combine my TFs. So I have a negative 416 TF and a negative 1337.3 TF. So on the same side of the equation, I want to combine them. So adding these two negatives gives me a 1351.016 temperature final value, TF. Okay, that's a negative. I added two negatives. Now I'm going to add the two non-TF numbers together. Okay, that gives me 60,795.72. No unit. And of course that's going to equal 130.72 TF minus 1307.2. Okay, let's keep on rolling with the simplification, changing inks because I can. I am going to move this positive 1307.2. Of course, that's going to cancel on this side. What I do to one side of an equation, I do to the other. And that becomes 1307.2. Let's go find that value. And this gives me, when I add these two together, 62,102.92. Okay, and of course I am now going to combine the TFs. So this is a positive 1351.016 TF. And I'm doing it to both sides for the same reasoning. Okay, this of course is going to cancel, and now I have 1 to positive 1351.016 TF. Let's go see what that gives me. Okay, make sure we know our equal sign still remains. It's just separating, and we add these together, we get 1481.736. Okay, and of course that is a TF. Easy to forget some details. So we're going to solve for TF. So it's going to be 62,102.92 divided by 1481.736, and that's going to equal my TF, temperature final. Okay, that gives me 41.912 degrees Celsius, which we can round to 41.9 degrees Celsius with 3 sig figs, and that is our answer. Okay, what is the temperature change for the block? By the way, we solved for the final temperature for both. okay, because they're going to achieve the same equilibrium temperature, okay, water giving off the heat and the block absorbing it. So let's go find the temperature change of the lead block. The lead block initially was at, I believe, 10.0 degrees Celsius. There it is. So 10.0 degrees Celsius. And the final temperature is 41.9. So to keep everything positive, I know that in some places you're going to put negatives to this, but we're going to keep everything positive in this course. Okay, we'll talk about thermodynamics in another course, but 41.9 minus its 10.0 degrees Celsius. That temperature change is 31.9 degrees Celsius. And the next one, water is at 45.0. So 45.0 was its initial temperature, which is bigger because it lost energy, and it became 41.9 degrees Celsius. And that gives us a 3.1 degree temperature change. The temperature change, of course, is far greater for the lead block because of its lower specific heat. Okay, lower the specific heat, the greater the temperature change, and which means it doesn't require a lot of energy to change 1 gram, whereas the higher specific heat chemical, the water, requires a lot more energy to change the temperature. Since the lead in the block, okay, or essentially the same amount of energy being released and absorbed, it's not quite the same because we have the cup involved here in this case. Oh, you can clearly see that the specific heat factor changes things. Okay, last part, what's the temperature change for the cup? That would be the same as the water, so 3.1. We can make that assumption the cup is sitting in the water for a long time. Okay, how much energy did the water release? Well, looking specifically at the water values, we'll rewrite them. 320 is the grams of water. Okay, so Q of the H2O is equal to, okay, M, which is 320 grams of water, which is the M. The C is 4.18 joules per gram per degree Celsius. And the temperature change of the water, okay, is 3.1. Okay, we wouldn't put the final temperature in the temperature change, and we come up with our values, which I get a raw number of 4146.56. Of course, that's going to be joules because everything cancels, as we've talked about. Oops, got my unit there. All right, and then of course I'm going to basically reduce this or round it to, I should round it to three significant figures. That limits my problem. Or is it 2 significant figures? Well, my measurements up here, my initial measurements, all are limited by 3 significant figures. So I'm going to round this to 3, and I'm going to make this 4.15 kilojoules. Right? I just converted the kilojoules here. It's what we normally do with a big number. Okay, and it's 3 significant figures. If you left it in joules and you wrote 415, 0 joules, same answer. Okay, and that's how we do this problem. It's essentially the same as the first problem, except now we added one more factor, and that was the cup. But there's only 2 sides of this coin. There's a side that absorbs and a side releases. So as I add more things into this thermal diagram, they're only going to go on one of 2 sides. There's going to be the energy release team and the energy absorb team. And we're going to see more and more of this as we go further. The homework that I'm continuing on with this tonight, or the worksheet that follows, I'm adding even another factor to the mix. But again, there's only 2 sides. The problems are essentially the same when you think about them. Okay, hope that helped.